This video is going to help you solve question 4 on worksheet 1 of unit 6 about energy. This is the question about the dart being pressed into a toy gun and then fired straight up. I've already pre-drawn 4 state diagrams, just really quickly to show you the states. The dart is in the gun and the spring is already compressed to its maximum push in. The dart is just emerging from the gun. The spring has fully unloaded its energy. The dart is at its maximum height. The dart is coming back down and is 1 meter above the ground. Okay, I'm going to walk you through how I solve this problem, and I encourage you to pause the video when you get to a point where you're unstuck so you can solve it for yourself. Let's start by just qualitatively going through and figuring out the energy of different stages. In this stage, the dart's not moving and it's at a height of 0. So I'm going to say 100% of the system energy is tied up into the elastic storage mode. In the second state, the spring has been fully uncompressed and the dart is just emerging from the gun. I'm going to consider the height of the dart at this point 0 meters, even though it's a tiny bit higher than it was here. It's close enough that it's a reasonable approximation. So these are zeros, by the way. So all the energy in the system is now kinetic. In this state, we're at our maximum height. No kinetic energy, the dart is not moving. Percent of the system's energy is tied up into the gravitational positional storage mode. Finally, the dart's coming back down. It's moving, and it does not have a height of 0. Those are the 2 types of energy we need to consider. I don't actually know right now if I have a 50-50 split here or what. We're going to come back to the exactness of that later, but all the others are straight up hundreds or 0%. This is going to help us find a path through solving the problem. Let's look for the type of energy that we can calculate first. So when I look through the information I have, I don't have enough information here to find the elastic energy because I don't know the K of this spring. I don't know how fast the dart is moving here. Don't have enough there. How high the dart is, I know its mass, and this is a good place to start. This is h at 0.2. I've already pre-calculated that out. That came to about 2, I'm going to make an approximation here just to make my math a little easier, 10 for J. And that's going to give me 2 joules of energy in this state. Now I'm going to use that to start filling in some other information. So with 2 joules of energy that are gravitational here, no other types of energy here, 2 joules. Now let's work backwards. I want to think about energy flow coming in or out of the system. I'm considering the dart with the spring inside it, and the gun, and the earth. Everything is inside my system. There's no energy flow right now in or out of the system. That means this 2 joule system here is still here. And back here, also no energy flow in or out, so 2 joules. Let's go forwards. No energy flow in or out of the system, still 2 joules. With only one type of energy here, I know that this is also 2 joules. Okay, let's see what I want to solve next. One of the questions asks me for the spring constant, and this is the only case where elastic energy matters. Spring constant needs to happen over here. The spring was pressed in for 2 centimeters or 0.02 meters. Now again, I've pre-calculated that. This solves to a K 1,000 newtons per meter. That's one of the subparts of the question that gets asked later. Another question is, how fast is the dart moving when it exits the gun? I'm going to use this case here because that's the state that we're talking about. When you solve this algebra, you come up with an exit velocity from the gun of just a little above 6 meters per second. And then the final question asks us about the work that goes into compressing the spring. So we want to think back here. Prior to us coming on the scene and seeing this state, somebody had to compress the spring. And if you picture that previous state, right before here, there's an energy flow into the system. So the work coming into the system in this first state here is going to equal the total amount of energy in the system right there. Okay, 2 joules of energy in the system right there. That 2 joules must have come in as work just prior to that initial state. Okay, so that's how you solve this problem. Good luck.